Okay, so section 1.2, this is the symbol for section, by the way. Section 1.2 is about, well, it says mathematical models, but the thing that is most important to me is that it provides a catalog of what they call essential functions. So that's really all I want to do, is just go over the sort of essential functions that I want you all to know as we move forward through the course. And so the very first type of essential function are linear functions. Now, I have no doubt that you all have seen linear functions before in the past. They look really simple. It's just you take your input value and you multiply it by a number, and then you add another number. So that is m and b. These are just real numbers. Okay. Sometimes the symbol that we will use for this is we'll say m and b. This is a symbol that means are elements of the real numbers. So m and b are elements of the real numbers. Anyway, so this is a linear function. So its graph, the graph of a linear function, is always a line. So graphs of linear functions are lines. Okay, and here's just the schematic for how that works. So here's a pair of axes, x and y. They're really easy to graph. All you really need are 2 points, but let's start with b. So the value when x is equal to 0 will just be b, right? Because m times 0 is 0, and then you add b. So the output when x is equal to 0 is b. And then the graph of this linear function will pass through this value on the y-axis, and it will be a line, and the slope of the line will just be the number m. So here's a picture of the graph of a line, for instance, and if you take any 2 points and you calculate the ratio of the rise to the run, the rise over the run should be this number m. Okay, so that's linear functions. Let's do a really, really quick example. How about f of x equals, I'm just making this up, 2x minus 3. Okay, here's how you would graph this without the use of your calculator at all. Like I said, we're going to allow calculators, but let's just, so where's minus 3? On the y-axis, it's right there, and let's throw in a few more. I'm going to mark off some integer values here. So usually when I mark off numbers on these axes, they're integer values. So so this is a line that passes through minus 3 on the y-axis and has a slope of 2. So for every one value that you go over in the positive x direction, you should go up 2 in the y direction. So that's it. So this point right here, this will be at the x value of 1 and the y value of minus 1, and then our line looks like this. It just passes right through that point, like so. So this is the graph of y equals 2x minus 3. Okay, another essential function, or essential, I guess this is a class of essential functions. Really, lines are contained in this next class of functions, but, well, whatever. So polynomials, so hopefully you all know what polynomials are. Polynomials, let's write down a bunch of them. So I'll give them little numbers, p1, p2, p3. These are just examples. Examples of polynomial functions. So here's an example. How about x raised to the third power plus 2x squared minus x. There's an example of a polynomial. How about 4x to the fifth minus 2x plus 17. Here's another example. I'm just making these up. 3x to the 18th power minus x squared plus 2.1. Okay. So in general, they look like this. I'm going to throw some notation at you here. Okay, so this is a general polynomial function. It has a highest power of x that occurs, n. This is called the degree. N is always greater than or equal to 0. It's some number that's greater than or equal to 0. These numbers starting at a0, a1, a2, all the way up to an. Here we pretend an is not 0, because if it is 0, then this isn't there. These are called the coefficients. These are called the coefficients of the polynomial. Okay, and so that's polynomials. Let's take a look at a few behaviors of certain polynomials. So here's I'm just going to draw some graphs. Here's something simple. How about the graph of the polynomial y equals x squared? So this looks like this. Okay, you've probably seen that before. How about y equals x cubed? So this is y equals x cubed. These are called, I think somebody said this in class last time, these are called quadratic polynomials, and these here are called cubic. Okay. Now, if you're looking at any other power of any other function that's a power of x, will look kind of like one of these two, depending on whether or not it's odd or even. So, for instance, so if y equals x to the n, and n is even, then the graph is basically going to look like this. Okay. The higher this power goes, the sort of the fatter the base of this goes. And then similarly, if it's odd, so this is y equals x to the n, where n is odd. And all that really happens is that the higher and higher you make that n in value, the more and more horizontal the graph will look at this point. But in general, when n is odd, it has this behavior, and when n is even, it has this behavior. All right, polynomials. Another class in our catalog of essential functions are power functions. So these are where x occurs to a power. So this is our function here. So a is just a number. Let's give it, well, we'll just call it a constant for now. We'll see what happens. Okay. When a is equal to 0, this is just the constant function, f of x equals x to the 0 power, which is just 1. And so this is just a graph that has height 1. When a is a positive integer, like 1, 2, 3, 4, 5, and so on. When a is a positive integer, then it just looks like what we had before. There's x to the 1, x squared, x cubed, x to the 4th, and so on. What's more interesting is when a is equal to 1 over a positive integer. So how about a half, 1/3, 1/4, and so on. These are, so x to the 1/2, that's a half, okay, x to the 1/2, x to the 1/3, x to the 1/4, and so on. These are probably better known by the symbols. This is the square root function, this is the cube root function, this is the fourth root function, and so on. Okay, so the graphs of these, well, they look very similar to the graphs of x squared, x cubed, x to the fourth, just tilted. So if we're looking at the graph of x squared, or sorry, the square root of x, this is y equals the square root of x. If we were looking at the graph of, say, y equals the cube root of x, also look like this, but the domain of this function will actually be all the real numbers. Whereas before, I suppose we should look at this for just a moment. The domain here is just positive, well, non-negative, real numbers, the domain of this, because there's no number that when you square it gives you a negative value, so you can't you can't take the square root of a negative number. Okay, so this is when a, the example when a is 1 over a positive integer. There's one other very important example, and that is when a is -1. So in this case, our function would be x to the -1 power, and we usually write this as 1 over x. The graph of this function is pretty easy to draw. It looks like that. It passes through the point 1, 1 right there, because when you put 1 over 1, you get 1, so it should pass through that point. And the closer and closer x becomes to 0, the higher and higher the output values of this are, because 1 over a small number is very large. And by the same reasoning, if you travel outward on the x-axis, then your output values are 1 over a very large number, so that will be getting very small. So this function approaches the x-axis in the long run and approaches, well, it just keeps climbing in the long run towards 0. This graph has symmetry to it because, so this graph has some symmetry to it, so it will pass through the point -1, -1 right here. And if you were to look along this 45-degree inclined diagonal line with negative slope here, this would look like a reflection. So this is the graph of 1 over x to the, or 1 over x. Okay, another class, where were we? I think 4, rational functions. Rational functions are very simple. They're just what you get when you take a, let's call this, we'll give it the name R for rational. It's what you take when you take a ratio of 2 polynomials. So these are both polynomials. And so you can probably construct lots of examples of rational functions on your own examples. We'll number them again. We won't draw any graphs of these. X squared minus 1 over x to the 4th plus 2. Here's an example. Here's another example. I'm just making these up because we know how to make polynomials, so we can easily just come up with a rational function. How about x plus 2 over x minus 3. All right, how about something like x cubed plus x squared plus 17 over x squared minus 4. Okay. And now the important thing to know about rational functions are the domain. The domain of a rational function is just all numbers for which the denominator is non-zero. So domain all numbers except those that make, so q, we were calling the denominator q of x equal to 0. So let's just do an example. Let's look at these examples. So here, no number makes x squared, x to the fourth plus 2 equal to 0. So the domain here is all real numbers. Again, this is the symbol that I use for the real numbers. This is the symbol for real numbers. Okay, it looks like an R, and then you just draw another slash through the R. Okay, the domain for this one here is all real numbers except for 3. So x equals 3, not allowed. And the domain here, well, it's whatever doesn't make the denominator 0. So the only numbers that make the denominator 0 are 2 and minus 2. So maybe if we wanted to draw a picture of this, we would do something like we would indicate minus 2 here. Here's 0 and 2. And we might go like that, okay, to indicate the domain. Or you might say the domain is all x that are less than or equal to 2, and well, how about or? There's no less. No, let's just redo this. So x has to be strictly less than minus 2, or x has to be strictly in between 2 and minus 2, or x has to be bigger than 2. So I'll accept any of these forms of the domain of a rational function. Technical difficulties. Okay, there are 2 more essential function categories. I guess we were in 5. I don't care what the numbers are. Algebraic functions. These are functions that you get by taking all combinations of plus, minus, multiplication, division, and roots of polynomials. So examples. I'm just going to write down a ton of examples. Algebraic functions, so here's a combination of, so we took x squared plus 1, and then we took its square root of that whole entire quantity, and then we add another polynomial. How about x cubed minus 2x to the fourth plus 7? And then we're going to divide this whole thing by, I don't know, how about x to the fifth times x cubed plus the fourth root of x squared plus 7, and something like that, and then we raise that to the second power. So you notice what I did here. This is just raising polynomials to power, adding them, subtracting them, that kind of thing. You could obviously make these very, very complicated, but all you do is take polynomials and then this set of operations, and that generates all of the algebraic functions. Okay, so that's algebraic functions. Trig functions. This is, for now, this is the last class. I guess that would be 6. This is the last class in the catalog of essential functions that we want to know. So I just want to talk about the sine function, the cosine function, and the tangent function for now. Okay, so let's define these. You've certainly seen these before in your pre-calculus class, or maybe you took trigonometry in high school. Students, in my experience, are kind of intimidated by these functions, but they're actually not that bad as long as you think about them the right way. So here's how I think about them, and hopefully this will help you guys through it. So this is just a circle with a radius of 1, centered in the xy plane at the origin. Okay, so this is just a circle. So now what I would like to do is I'd like to define the sine and cosine functions using this unit circle. So here's what you're going to give me the input of this. It's going to be well, you tell me the input, and then I will measure out. Exactly starting at in the direction of the positive x-axis, an angle that measures the input value you gave me. So maybe let's use a Greek letter here for this. How about theta? Okay, so this is the Greek letter theta. So you give me the input, which we'll just call theta, and then I want to use that as an angle, and so this is maybe we'll measure this in radians, measured from the positive x-axis. So if theta is positive, then you're going to go this way. If theta was negative, we would go that way. But anyway, so what do we notice about this? Well, this is a radius 1. This is a radius 1 circle, so the length of this segment right here is 1, and then if I look right here, I've got an x value. Let's just call it a, and then I've got a y value. Let's just call it b. Okay, so the coordinates of this point here are a and b. Okay, now here's the definition of sine. So sine of theta, so the sine of this angle right here, is just the y value, the y coordinate of that point. The cosine of that value is just the x coordinate of that point. So that's it. That's all there is to it. I almost basically don't have nothing else to say about this. So the tangent of theta is defined, this is its definition, it's defined to be the sine of theta over the cosine of theta. So that is just b over a. So these are the definitions. Okay. So now let's go through just a little tiny bit of review about the unit circle and measuring radians around the unit circle. Okay, so this is again, my circle looks like it's had a pretty bad night here, but bear with me. So if we are inclined here, this right here is theta equals 0. This right here is theta equals, I'm trying to do 45 degrees. We don't use degrees though when we're in calculus. We use radian measure, and so this here is pi over 4, otherwise known as 45 degrees, but your calculator will tell you pi over 4. Right here, this is theta equals pi over 2. This is 3/4 of the way to pi, and this is pi right here. So if you went all the way around like that, if that was, then you would be at pi. Now notice, so we know what the coordinates of these points are. The coordinate here is -1, 0. The coordinate right here is 0, 1. The coordinate right here is 1, 0. And if you put a little bit of thought into it, you could probably figure out the coordinate right here is the square root of 2 over 2 and the square root of 2 over 2. Okay. similarly for points all around here. But now that we know what all of the coordinates of these things are, maybe we'll just fill this one in. It's minus root 2 over 2, root 2 over 2. Now we can figure out what the sine and cosine are of any of these angles. So the sine of pi, for instance, well, pi is what? You go all halfway around the circle, and you look at the y-coordinate right here. So the y-coordinate is equal to 0. The cosine of pi is the x-coordinate there, so it's minus 1. The cosine of, let's try pi over 4. So pi over 4 is this angle right here. It's just the x value, so it's root 2 over 2. The sine of 3 pi over 4, so it's sine, so we look at the y-coordinate at 3 pi over 4, 3/4 of the way, halfway around, and we look at the y-coordinate, it's root 2 over 2. Okay, so the cosine, for instance, of pi over 2, well, pi over 2 is 1/4 of the way around the circle, so the cosine is the x value there, it's 0. The sine of pi over 2 is 1 because the y-coordinate there is 1. Okay, so that's how you do trig. All right, now we want to look at the graphs. Okay, so I want to talk about the graphs of these functions, sine and cosine. So you'll remember that, that this is the unit circle here, and if this is our input value, x, it's just an angle in radians, then the coordinates of this point right here are cosine of x and sine of x. So this is the definition of sine and cosine. Now, if you think about that, let's draw the graphs of, let's say, sine. We'll try sine first. So here's x, and then we're going to draw the graph of y equals sine of x right here. So starting off, when x is equal to 0 at this point, that would be an angle of 0. So you see this bar would be down pointed in the direction of the positive horizontal axis. And so the sine value would just be the y-coordinate right here. So that's equal to 0. Okay. Now as the x value increases here, that corresponds to increasing that angle of inclination there. And what's happening to the y-coordinate of the point as you drag this up here? It's increasing, and it's increasing to 1. So by the time we get to, let's say, pi over 2 here, which would correspond to this point on the unit circle, we should be at 1. So we'll put 1 there. And so what will happen is that as the x value ranges from 0 to pi over 2, so as this angle of inclination goes from pointing directly to the right to pointing straight up, the point on the y-coordinate should rise to be 1. Now what happens after that, as this point gets dragged down to pi, there's pi, the y-coordinate decreases again back to 0. And so we get that, okay? And the same thing holds, so it takes, you have to go once around the circle for this to happen. This is 3 pi over 2, and this right here is minus 1. So this is the graph of y equals sine of x. And this will just repeat over and over again, and the reason it repeats, oscillating between +1 and -1, is because as you take this point and drag it around the circle, the y value never gets bigger or smaller than + or -1. So this is the graph of the graph of sine. The graph of cosine is very similar, and the graph of tangent as well. The graph of tangent we'll discuss in class.